welcome to your weekly algebra recording. We are in week 5, and it is also the week of February 7th. I do have a warm-up question this week, as I always do. It's a little bit different. What I want you to do at this time is to open a new window, log into algebra, and I want you to look at what your current grade is in the class. I want you to be aware of where you're at, and we are still early on in the semester, where right now you can make some big improvements to your grade pretty quickly. Remember, the further the semester goes on, the more points the overall class is out of, and the harder it can be to get your grade where you want it to be. So now is the time to be proactive. So check and see what your current grade is in the class. If it's less than 70%, I want you to start thinking about some ways that you can improve your grade. Increasing the amount of time you're spending working in the class, getting caught up with any outstanding assignments. So looking through your grades tab to see if you have any missing assignments, and getting those missing assignments submitted as soon as possible will help. So just want you thinking about where you are and where you want to be with your grade. All right, so this week you're going to spend some time reflecting on how you're doing in the class. We're going to take a look at what you've studied in this unit that we're working on right now, and we're going to also do that in the recording this week. And then you're also going to take the unit test. So what is the title of the unit we've been studying? So the title of the unit that we've been studying in Edgenuity is Exponential Functions, Radical Functions, and Rational Numbers. So let's think about that title for a moment. Exponential functions, this is what we started the unit with. So we talked about how we can have exponential growth and decay equations, and we're going to review that. Exponential growth and decay functions. We talked about radical functions. We learned all about radical functions. We learned about cubed roots, and we learned about square roots and how we can rewrite each of those as having exponents. We learned about operations with rational and irrational numbers. So that is just a quick summary of what we've learned in this unit based on the title. So just to get us thinking back about what we've learned in this unit. So let's jump right in and do a quick review. So remember, this is a quick review. There's no way for me to go over everything you guys have done in the past 4 weeks. So this is just a really quick review to get your minds thinking back of what all you have learned. But remember, when you study for the unit test, you do need to go a little deeper than what we are right here. This is just a beginning to get you thinking about everything you've learned in this unit. So we started with exponential functions. So I'm going to start with the equation of an exponential function, the general equation. Now, these are just letters, and we can substitute the letters with numbers, of course. So an exponential function, the most important piece is that we have a variable as our exponent. That's what makes it an exponential function. So some important bits here. This b term right here, this term right here, this represents if we're going to have exponential growth or decay. And how we know that is if the letter b is greater than 1, when we've got a number instead of the letter b, if that is greater than 1, then that equation would show exponential growth. And that's going to look like that when we graph it. If b is less than 1 but greater than 0, so it's going to include all of our decimals and fractions, we would have exponential decay. So our graph is going to decrease over time. The decrease starts slowly, and then over time the decrease grows rapidly. And then we also have, let's do this in a different color here, the number that we can substitute in for A. This represents our starting point, or we can think of it like as the initial amount, initial population. It's our starting point. So if we have, let's do a little example. I'm going to draw a line in here and do an equation for us to practice with. If we have an exponential function such as 2 times 0.5 to the x, who can tell me what 2 represents? What does that number 2 represent? Well, it represents our starting point, that we start with 2. That's our starting point. What about 0.5? What does that represent? 0.5 tells us that we've got exponential decay, and that each time, as time goes on, if we're talking about days, that we will have a multiplicative rate, I ran out of room, multiplicative rate of 0.5. So if we start with 2, so our initial amount would be 2. So if our x value is 0, our initial amount, our y value is 2, our initial amount is 2. Then after 1 day, if we take 2 and multiply it by 0.5, we get 1. So what I'm doing is I'm multiplying each previous value by 0.5. And we can see that that's the multiplicative rate is 0.5, showing we've got exponential decay. And if we were to graph this, we're going to see that our graph looks something like that. So just a very overview of exponential growth and decay. This example here happened to focus on exponential decay. So we can use a table to represent an exponential function. So here, our table, here's our x values and the corresponding y values. So we always start with our initial amount. So our initial amount here is 4. And then how are we changing from each data value? So it looks like we're going from 4 to 8, and then 8 to 16, 16 to 32. Do you see a pattern there? We're multiplying, we're doubling each time. So each time we are doubling. So our multiplicative rate here is 2. And in order to have an exponential function or a function that grows exponentially, you have to have some kind of multiplicative rate between your y values. So if you're adding 2 each time, that wouldn't represent an exponential function. It's got to be an amount that is multiplied by a certain value. So we could actually write the exponential equation from this table. It would be, since the initial amount is 4, that's our starting point, we know the multiplicative rate is 2, and then we put our x as our exponent. So that is exponential functions. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. All right, we also learned about exponential functions with irrational bases. So we learned that we can go from writing a radical and rewriting it with just having an exponent. So for example, if I have here the cube root of 7, I can rewrite this as 7 to the 1/3. So what we notice here is that the this number right here is the denominator of our exponent. So look at this one, it's a little bit different. We're trying to find the cubed root of 125, all raised to the x power. So let's ignore this exponent of x for just a moment. Let's ignore that for now. Let's just rewrite the cubed root of 125 as an exponent. So the cubed root of 125 is going to be 1 over 3. There's the our radicand here, and then here it is 3 as well. So, but we also have all this raised to the x. So instead of having a 1 as our numerator, we're going to change that to an x. And it's rewritten. Last but not least, let's simplify f of x equals 81 to the x to the 4, x over 4. So x over 4 is the power. So first of all, can we rewrite, let's say we just have 81 to the 1/4. How can we rewrite that with having a radical? Well, it would be the 4th root of 81. And remember, this little number 4 here tells us that we're trying to find what number multiplied by itself 4 times equals the number underneath the radical, which is 81. So that little number 4 lets us know we're trying to find the 4th root, or a number multiplied by itself 4 times gives us 81. So what would that be? So let's try, I'm just going to start low here. Let's try 2. 2 times 2 times 2 times 2, and let's see what happens. 2 times 2 is 4, times another 2 is 8, times another 2 equals 16. So we're definitely low. What else might we try? Maybe 4. 4 times 4 times 4 times 4 gives us 256. So what about 3 times 3 times 3 times 3? So that, let's try 3 times 3 times 3. 3 times 3 times 3 times 3. 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81. So I know that 81 to the 1/4 is the same thing as 3 because, or yes, 3, because 3 times 3 times 3, 4 times itself 4 times gives us 81. But then, so we've taken away this 8 and the 81 to the 1/4, but we still have that x in our exponent, don't we? We still have this. So now all we need to do is just set it 3 to the x. So our final answer would be 3 to the x. Because we first, again, to kind of summarize what we did here, the first thing we did was we evaluated 81 to the 1/4. We kind of held on to this x, put it aside for now. We knew that 81 to the 1/4 is the same thing as taking the 4th root of 81, which we found was 3, and then we had to bring that x back into our equation, 3 to the x. So just some practice of going between radicals and exponents. Remember, we need to practice that. So going on to the next slide, so if you need more time, go ahead and click pause. We also learned about geometric sequences. So remember, a geometric sequence is just a sequence in which the ratio between any consecutive terms is constant. So remember, a ratio is when you, it's something like comparing two numbers. For example, we use a ratio to find the common ratio for a geometric sequence. And we can find a common ratio by dividing one term divided by the previous term in the sequence. So you pick a term such as 18, and then we're going to find the common ratio, we're going to take 18 and divide it by the previous term, which is 6. And 18 divided by 6 is 3. So the common ratio should be the same for all of the terms that we do this same, we use the same pattern. So for example, let's check another. We could take the number 6, and we're going to divide it by the previous number, which is 2. So 6 divided by 2 is 3. We're getting the same ratio, that it's 3. We could take 162 and divide it by the previous number. 162 divided by 54 equals 3. So a common ratio, in order for a sequence to be a geometric sequence, we have to have a common ratio, or we have to find that when we take one number and divide it by the previous number, we get the same number. We get that same ratio. So look at number 2. Do these numbers, do they represent a geometric sequence? And if they do, what is the common ratio? So if you want, you can click pause and try this on your own. All right, so what I'm going to do is I'm going to take 40 and divide it by 160 and see what I get. I'm going to change colors here just so it's not as confusing. We're taking 40, dividing it by the previous number. So I know I can cancel out my zeros, and 4 divided by 16 reduces to 1/4. So the ratio between 40 and 160 is 1/4. Then I can try it with 10 and 40. See if I got that same 10 divided by 40. I can divide out the zeros, left with 1/4. So it looks like we're seeing that I can do it one more time. 2.5 divided by 10, 2.5 divided by 10. If I divide those numbers out, I get 0.25, which I know is the same as 1/4. So these numbers do represent a geometric sequence because I get the same ratio when I compare a number to the previous number in the sequence. And my common ratio would be 1/4. 1/4. I'm going to go on to the next slide and talk about recursive formula for geometric sequences on the next slide. All right, so in geometric sequences, we also learned how we can write a formula, a recursive formula, to figure out what the next term would be in a geometric sequence. So for example, first of all, here is the recursive formula for a geometric sequence. So if you start with the first value, x, and we want to figure out what the next value is in our sequence, that's why we say x plus 1, to say we're trying to figure out what the next value in our sequence will be, what the next number will be in our sequence. So that's where that plus 1 comes from. R represents the common ratio. So R, I'm kind of running out of space here, represents the common ratio, which is what we just looked at on the previous slide, the common ratio. And then f of x, that represents the first term in the sequence. So f of x represents the first term in the sequence. So that is what everything stands for. So now, if we have a sequence of numbers 2, 6, 18, 54, first of all, what is the common ratio in that sequence? We'll take any number in the sequence and divide it by the previous one. So if I take 6 and divide it by 2, I get 3. If I take 18 and divide it by 6, I get 3. So the common ratio is going to be 3. So now that we know the common ratio, let's write the recursive formula. So I'm going to follow this guide up here. This is the general equation for the recursive formula. So I'm going to take f of x plus 1, set it equal to, remember R represents the common ratio, which we know is 3. F of x represents the first term in the sequence. What's my first term in the sequence? Right there, it is 2. So I'm going to write 2 times 2. And I got a little bit ahead of myself. I don't want to put 2 in there. I want to put the f of x in there instead. So we're going to have f of x times the common ratio. So this would be the number the previous number in our sequence. That would be our previous number in our sequence. So I moved our formula over here so that we can try this now. So we know the first term is 2. Now let's try and see if our formula works if we want to find the second term. So if we want to find the second term, we are going to put in so we would, let's go ahead and actually, I'm going to start over here. Let's try f of 1. So f of 1, we know f of 1 is our first term, which we know is 2. Now, if we want to find our f of 2, remember that's going to be x plus 1. So that would be our f of 2. And we're going to set it equal to 3 times f of 1. And we know our f of 1 was 2. So f of 2 equals 6. And that's our second term in there. If we want to find our third term, we would take 3 times our f of 2. And we know our f of 2 is 6, which would equal 18. Our third term is, in fact, 18. So that is how the recursive formula works. And next, we're going to take a look at the explicit formula for geometric sequences. So here's the formula where we have f of x equals f of 1, which is going to represent the initial amount, times r, which is again going to be the common ratio, and then x minus 1. So let's use this formula to answer the question below. So what is f of 5 if f of 1 is 3.2 and f of x plus 1 equals 5/2 f of x. So if you look right here, what are we given? We're given the recursive formula. We're given the recursive formula, which we used above. And we know there's some pieces that we can take from this. So from the recursive formula, I spelled that wrong. From the recursive formula, can you identify what the common ratio is? Can you tell me what the r value is, or the common ratio? So remember, the common ratio is being multiplied by the f of x. And I see that number. Let's get rid of that. So here's our r value right there. So our r, which is our common ratio, is 5/2. It's 5/2. And now we want to write the explicit formula. So we want to substitute some values in so that we can write the explicit formula. So we know we've got f of x, and then next in the formula is f of 1. Well, that's given to us. F of 1 is 3.2. And then we also figured out the common ratio because we were given the recursive formula. So that's going to be 5/2. And then next, we just put x minus 1. And now we're done. We've written the explicit formula for geometric sequences. And we can use the explicit formula, remember, to find like the 20th value in our sequence. So if we're trying to find the 20th term, we would use this formula. We would plug in 20 for x, and that would tell us what the 20th term is in this geometric sequence. So I'm going to go into the next slide. We also learned about, I'm going to stop going into a detailed review because I am already at 24 minutes and I want to keep this under 30 minutes for sure. So you're going to need to spend some time reviewing square root functions and cubed root functions in as well as the graphs and what the graphs look like. So you need to review cubed root functions and square root functions. You also need to review on your own operations of rational and irrational numbers. And that is really it. So this brings us to the end of our key phrase, or end of our recording for the day, which means it's time for the key phrase assignment. So we went over a lot of different things today that you learned in this unit. I want you to tell me 3 things we reviewed. That should be an ED. Reviewed today. So tell me 3 things that we reviewed today. Directions are always included at the bottom if you need a reminder of how to complete the key phrase assignment. Otherwise, have a wonderful rest of your week and let me know if you need any help with anything. Remember, I'm here to help. Have a great rest of your week.